to have that honor. All right. Well, this is the surprisingly simple tech behind digital cinema by Pete Sengstock. Pete is currently the Director of Media Services for the Department of Communication Arts and has been working there in various capacities for almost 2 decades. ComArts is home to the Wisconsin Center for Film and Theater Research, UW Cinematech. Cinematech? Pete, is it Cinematech?
Yeah, you got it.
Awesome. Cool. I wanted to make sure that I didn't get the pronunciation wrong. And Commerce is also home to the Wisconsin Film Festival, which I can personally recommend and is one of the most foremost authorities in critical film studies and film history worldwide. It's also home to the ComArts Instructional Media Center, which supports its well-regarded media production program. We will have time for questions at the end of this session, but without further ado, the surprisingly simple tech behind digital cinema.
Awesome. Thanks. And just to preface, this presentation largely focuses on 2K and 4K digital cinema and the more conventional projection and distribution systems. There's a number of other technologies using digital cinema and many formats beyond what's discussed in this talk. This talk is intended to be a deep, narrow dive into the technology to gain an appreciation for it and hopefully have some fun along the way. Let's first start with a little history about cinema. Cinema grew out of our sheer fascination with the moving image. Early actuality films would show things like a train arriving at a station or a couple kissing, and they would draw throngs of patrons willing to pay a nickel to see this new novelty. From there, it steadily refined its methods, developed its own language, and eventually evolved into the countless genres and styles we know today. Over the decades, cinema continuously pushed against the technical boundaries around it, breaking new ground and establishing new tools and techniques with the goal of drawing in audiences and keeping them spellbound, among other things. Film had been around for over a century, but it wasn't without issues in the minds of distributors. It was expensive to produce, expensive to ship, and very vulnerable to wear and tear if mishandled. But what if they could remove film from the distribution process entirely? In 2002, these 7 motion picture studios, MGM, Sony, Universal, Paramount, 20th Century, Disney, and Warner Brothers, formed a consortium called the Digital Cinema Initiatives LLC to tackle this very question. You might recognize their acronym from DCI P3 compliant displays. Yep, same group. DCI knew hard drives were the future. If they could come up with a means of fitting an entire film onto a single hard drive, they could improve distribution dramatically. It would avoid image degradation due to media wear and tear. Making multiple distribution prints could be as cheap and easy as copying files. And getting a single hard drive to a theater was far less expensive than shipping films, heavy film reels. Last, they could encrypt these films, ensuring that they could only be screened when and where they decided. There were lots of distinct advantages for the studios and their distributors. Fun fact, the average 35 millimeter film for distribution is 2,000 feet long, which is about 22 minutes and weighs about 10 pounds. They ship 2 reels per can. So when you add up the film, the cans, and the reel weights, one film can weigh close to 50 pounds. Theater owners would ultimately get the short end of the stick in all this. They risked losing their access to new releases if they didn't upgrade their equipment. The upgrades were more expensive than conventional film equipment. To offset the upfront costs, integrators would leverage what they called virtual print fees, but those would just dig into profits for the theaters and leave fewer for them. It would also sadly spell the end for many projectionists. Let's talk about some cinema hardware. So first, you need a big projector, and not just any projector. It has to adhere to the DCI specifications for digital cinema packages, or DCPs. That includes the signal types, aspect ratios, frame rates, color standards, and the security. It uses huge short arc xenon bulbs, has liquid cooling for the imaging components, and a massive lens. It's essentially a bunch of glass with a bit of electronics sandwiched in the middle. Cinemas typically use a perforated screen because the speakers are mounted behind it and need to blast through it. While not unique to digital cinema, one common issue to overcome with digital is the moire pattern that's produced between the screen perforations and the individual pixels of the projected image. For that reason, they typically throw the image out of focus ever so slightly, though hopefully never enough to be noticed. Another fun fact, this projector in this image was one of three projectors that was donated to the Wisconsin Film Festival when the Hilldale theaters closed down. Here we were using it as a donor machine for another projector in Music Hall ahead of the 2006 Film Fest. The projector weighs 250 pounds, so we had to use studio winches to bring it to working height. For sound, there's usually a digital cinema processor. This takes the various specialty audio formats like Dolby Digital, Pro Logic, or even just straight PCM audio and passes it along to the amplifiers and the many, many speakers in the theater. Just like projectors, some of these speakers are big, as you can see from the photo here. Next, we have the Integrated Media Block, or IMB, which is arguably the most niche aspect of digital cinema, mostly because it's at the heart of the security chain. It's a modular component, but it needs to be locked in the side of the projector behind a tamper-proof cage. This is because the IMB is what handles the actual decryption and playback of the DCP media. The ports that connect to various alternative input sources, audio processors, storage devices, or cinema servers are exposed, but everything else, the board, the projector's imaging circuitry, and the wiring between them is literally under lock and key. Upon installation, the IMB and projector undergo a marriage process. You can see the marriage button in the image on the screen here, during which the secure state is established. If any tampering occurs to gain access to the unencrypted signal, such as unlocking the access panel, it'll break the marriage and disable playback. The IMB also introduces hidden forensic marks into the picture and or the audio and as it decrypts them, so that if anyone did manage to pirate the unencrypted signals, they could be traced back to the time and location they originated. The cinema server is the next piece of hardware. It's nothing fancy. It runs a Linux-based operating system, or rarely Windows. It includes a small storage array, which offers some redundancy for data, and typically has a PCIe or Ethernet connection directly into the IMB and the projector. It's what actually stores all the content and sends it to the IMB for playback. In many venues, the cinema server will also connect directly into other control systems, such that a single playlist on the server can trigger screen masking motors, lens adjustments, lighting presets, sound profiles, and the actual media playback order. More common these days is something that's called an integrated media server, which is actually like a combination of the IMB and the cinema server in one secure module that gets locked inside the projector. Actual cineplexes, big cineplexes, will go a step further and use a full theater management system, which is effectively a cinema server turned up to 11. It's capable of coordinating automation and scheduling of every single screen in the entire facility. A single ops center could effectively control all automation for every screen in an entire region of the country. For example, every Marcus Theater in the Midwest. Lastly, there's the humble crew drive. This is what's actually distributed to the theaters. It's nothing more than a SATA hard drive caddy. Its enclosure and host interface were originally developed for military use, but there's nothing else special about it. On the server side, it typically interfaces via eSATA or a USB dock or adapter. On the server side, the drive is formatted with standard Linux ext or sometimes NTFS. The internet delivery of DCPs is becoming more common, but the drives are still the workhorse of distribution even today. So now that we talked about the hardware, let's dive into the actual DCP, or digital cinema package itself. In 2005, DCI laid out the following specs for digital cinema packages. For the picture, they would use JPEG 2000 for each and every frame. For the sound, they would use pulse code modulation or PCM audio. Each of these track files would then be encapsulated into material exchange format, or MXF files. Those would be checksummed using basic security hash algorithm 1. And the layout of the DCP would be defined in some XML files. Finally, anything that needed encryption would run through standard AES encryption. JPEG 2000 was developed in 2000. For DCPs, DCI specified that each frame of film be encoded into a single JPEG 2000 image, as opposed to codecs like MPEG, which use temporal compression algorithms requiring keyframes and other reference point. JPEG 2000 uses spatial compression. This means that encoding for different resolutions and parts of the files is completely contained within each and every image file. This leaves very little artifacting at higher data rates. Another feature of JPEG 2000 is that it used progressive decoding. This means that the more the file you read, the more resolute the image is, or the higher resolution it is. Both of these examples demonstrate that to some extent. What's great about this is that it also means that image scaling is handled exactly within the file itself. No external hardware is required. For a 2K projector to play a 4K film, it just reads 1/4 of the file and then moves on. Now that wrong direction, sorry. In addition to format, the picture DCI also specified the aspect ratios and frame rates. DCI 2K and 4K are both a bit wider than HD and UHD respectively. This is partially due to the existing film aspect ratios of 185 to 1 and 239 to 1. The DCI spec allows DCPs to use the entire width or height of the capable projection area depending on the format, thus maximizing the resolution as much as possible. Frame rate is derived from the original cinema frame rate of 24 frames per second, or the many video standards, which in turn are bound to worldwide power standards. For example, 30 or 60 frames per second for 60 hertz power countries like in the US, or 25 or 50 frames per second for 50 hertz power countries like in Europe. The exception to this is that these are all hard frame rates. There is no 23.976 or 29.97 frames per second if you've experienced those. These are video frame rates that have a history tied to broadcast time clocks, power interference, and things that just aren't relevant in digital cinema. DCI also breathed new life into the concept of 3D cinema. Because they were now digital, it was no longer strictly necessary to project stereoscopic films with two projectors. They could still use the same techniques of polarized glasses, but DCP also allowed a use of a newer technology called active shutter 3D, which had gained some niche popularity from the 1980s through the 1990s, largely from video games, such as the Famicom 3D system. Active shutter 3D uses powered LCD glasses, which block out one lens at a time. They're synced with the shutter speed of the projector using an infrared signal that's blasted out into the theater. They also typically alternate the displays of each eye much faster than conventional 3D films would have. The result is an impressively crisp and eye-popping image. UW Cinematheque and the Film Festival regularly partner with the 3D Film Archive to show restorations of 3D classics, which again, in many cases are far superior to the original presentations. If you get the chance to see one, I highly recommend you take it. XYZ color space. These graphs show the CIE 1931 chromaticity diagram. CIE stands for the International Commission on Illumination. That's a mouthful, sorry. It's an idealistic mathematical representation of color vision relative to a normal human being's eye. And it's still referenced today at the heart of most all color standards. Half a century later, in 1980, a scientist named Michael R. Pointer sought to define a more realistic catalog of colors based on what we can actually see in the natural world. This became known as Pointer's gamut and is represented by the blobby area in these graphs. This excludes neons, computer-generated colors, and other unnatural colors. Later in 93, the International Telecommunication Union published the spec known as Rec 709, which was to be the standards for HD TV. When DCI was working on the specs for DCP in 2005, their goal was to capture even more of Pointer's gamut than HD TV did. Their new color space, DCI P3, also specified a gamma, which was more effective for reflected light in a dark theater environment, and a white point, which was more correct for the xenon light sources being used. Eventually, in 2012, ITU published a revised spec for UHD TV and one-upped everything with Rec 2020. Its goal was to finally encompass just about all of Pointer's gamut. However, there are still very few UHD TVs today that are capable of these full spectrum of colors outlined by Rec 2020, as a lot of these colors can't actually be produced without very specific laser light sources. Okay, let's finally move on to sound. Pulse code modulation, or PCM audio, dates back to the 1960s, and its ubiquity has helped it maintain a foothold in many media applications. WAV, AIFF, audio CDs, DVDs, most professional cameras. It's no wonder they selected it for DCPs. If it's not broke, don't fix it. PCM is a very simple method for converting analog to digital. You just sample the frequency of the signal at set intervals and store the resulting data. The higher the sample rate and the larger the bit depth, the more accurate the digital representation of the original waveform. For DCPs, they sample it at 48 or 96 kilohertz with a bit depth of 24, and they also use 16 channels for all that Atmos goodness. Another fun fact, the image on the left here shows an actual 35 millimeter edge soundtrack from motion picture film. The far left is DDS audio. The middle is Dolby Digital, which includes the little double D logo. And the right is just good old analog audio. Yep, that's what it actually looks like on film. Once we have our picture and sound files, we can finally start building our DCP. First, they're each encapsulated in their own material exchange format files. These are optionally encrypted with AES. Next, an XML file called a composition playlist, or CPL, is generated. The CPL defines the reels or groups of files that should be played together and the order in which they should be played. In addition to the picture and sound files, it can also refer to subtitles, closed captions, or even alternate picture and sound files. For example, original versus dubbed audio. This is how the Cinnamon server knows how to put everything back together. Let's look at a CPL snippet from the DCP I showed earlier. Here you can see that a reel has a UUID and it has an asset list that consists of a main picture track and a main soundtrack, each of which have their own UUIDs. The picture track is a frame rate of 24 frames per second. In here it's shown as 24 space 1, which is interpreted as 24/1. And it has an aspect ratio of 1998 by 1080. It also lists the duration in second for both of these tracks as well as their checksums. Let's talk about encryption. The picture and sound files for a DCP are optionally encrypted using a standard AES encryption, but using a symmetric key. The distributor holds this key and does not share it directly with anyone. Instead, they use asymmetric encryption and put that symmetric key inside a key delivery message, or KDM, using a public key pulled from the IMB within the projector. The theater provides their projector or IMB serial number when they book the film, and the distributor looks it up in the public database to get the public key. The distributor routes the DCP to the theater, separately emails them their unique KDM. When the theater loads everything to the server, it takes it from there. The KDM is only decrypted inside the IMB, and because this all happens within the physical lock and electronic marriage between the projector and the IMB, the symmetric key for the film is never compromised, and the content can only be played on the projectors that the distributor is explicitly authorized in that KDM. As a further layer of protection, the KDM also includes permitted time frame for playing back the film. This means the distributor decides the dates and times the film can be screened and ensures that it can't be shown months later if left sitting on the server. At the same time, if the film is successful and they want to extend the run, the theater doesn't need a new DCP, they just need to request a new KDM. Another fun fact is a common horror story traded around by film festivals about the debut screening of Brian De Palma's film Passion in New York in 2012. De Palma and others were in attendance, but as the film was supposed to start, a staff member came out on stage and informed everyone that the files wouldn't play anymore. The distributor had dutifully locked them down to the exact time of the screening, but in the wrong time zone. By the time anyone could figure it out, it was too late and they had to cancel it. So all the files, the picture, sound, CPL, subtitles, etc., are then checksummed using SHA-1 and cataloged in another XML file called a packing list, or PKL. The PKL will help the cinema server validate that the DCP is indeed intact and that it has everything it needs to play the film. Looking at the PKL file from our earlier example, we can see it first lists an XML file, which is our CPL. Next, both the picture and sound files are referenced. However, each of these are only referenced by their UUID. Most importantly, for each asset, we have a SHA-1 hash, the file size in bytes, and the type of file that it is. All that's left is some alphabet soup. That's the best way to describe DCP titles. However, they contain a lot of very pertinent information that can be used by the server to determine how to play things. What's the screen aspect, the lens adjustment, or audio setting that should be set? Is this an OV original version DCP with all the picture and sound, or is it a supplemental VF version file DCP that was issued with alternate audio, subtitles, open captions, or other content. Trained film festival projectionists can easily tell you most of what you need to know about a DCP from a quick glance at its title. Finally, we have our finished DCP. There's a couple other default XML files that are added at the very end of the process, but otherwise the entire DCP is just a folder with all the track files and a few XML files to tie it together for playback. Pretty simple. How does one make a DCP? Software like Adobe Premiere and Blackmagic DaVinci Resolve include paid options to export DCPs, but they're not great. Beyond that, the only way for small independent filmmakers to get their films to festivals was to shell out thousands of dollars for professional DCP mastering and distribution. Additionally, how were small film festivals supposed to test dozens or hundreds of films they would receive to ensure they were intact, without errors, in the right time zone, all those things? Open source to the rescue. DCP-O-Matic, great name, is free software anyone can use to produce their own DCP from just about any original files. It handles all the XYZ color conversion, the JPEG 2000 encoding, the file packing, checksumming, building the XMLs, everything. Here are some very basic steps to create your own DCP if you want to screenshot this. Every semester in ComArts, we hold a student showcase in collaboration with Wood Film at the Marquee Theater in Union South, and students produce their own DCPs for the show. You could even convert your own home movies to DCP and talk to the local theater about renting the space for a private screening. It's really, really easy. And we have the open source community to thank for that. DCP-O-Matic was created by Carl Hetherington, pictured here on the left, and is a household name among independent filmmakers and festival staffers. Additionally, Digital Cinema Tools by Wolfgang Vale is widely regarded as an excellent set of in-depth analysis tools for troubleshooting DCPs. These and other project contributors use the same basic technical specs I've covered here to create robust, easy-to-use, free tools that work. A good deal of the larger film community owes a debt of gratitude to these individuals. In particular, I think their work is a fitting counterpoint to the original goals of DCI, which were indeed centered around profits and control. So some takeaways. Understanding one technology can give us a frame of reference for others and empowers us to learn even more. With the ever-changing landscape of technology, it can be daunting to try and stay on top of everything. Staying curious and willing to explore a little at a time can help us break down a lot of barriers and continue to learn about the world around us. Change can come in different forms. You can look at it as a problem or a new challenge, and your outlook might help you with how you adapt. I'll bang the proverbial open source drum again. Take the time to recognize the work that open source developers provide to our technical lives. Thank them, support them with donations if you can, and if possible, contribute to the work yourself. And see more movies. The goal of this talk was not to get too into the weeds about the current state of the film industry, but instead to get people excited about the technology and movies in general. Movies are meant to bring people together, and sharing a movie with family, friends, or even complete strangers is part of the experience. At the end of the day, movies aren't anything without an audience. And that's my talk. Thanks.
Awesome. If we can get a round of applause for Pete in chat, I'm going to send a link to the DCP-O-Matic. Thank you so much, Pete, for this talk on a subject that and I'm sure that many of us are not familiar with. We do have time for questions. If there's anything that anyone's curious about, you can go ahead, put them in the chat or unmute and ask out loud.
Yeah, while we're waiting for those to come in, I've also got these additional references on screen. And just a brief aside, so David Bordwell was he's a prolific scholar, and along with his wife, Kristen Thompson, helped define critical cinema studies worldwide right from here in Madison. Well, he sadly passed away in 2004. His website is still maintained and contains a treasure trove of in-depth analyses and other aspects of film and media. So I'd recommend you check that out along with his free ebook, Pandora's Digital Box. Any other questions? Otherwise, I'll talk more about these references. If you're interested in exploring more about film and media history that exists right here on campus, you could look at the Wisconsin Center for Film and Theater Research. They house tons of items relating to film and television history, not just with ties to Wisconsin. They have cool things like the all the drawings from costume designer Edith Head and original script treatments for Jurassic Park, which was adapted by screenwriter and UW alumnus David Kep.
That is very cool.
Yeah. Um, Also, if you're interested on going to see more films, I recommend you check out Cinematheque, which is the free film program here on campus. They just announced their summer season, which runs late June to late July. All the screenings are free and open to the public. There's also Wood Film, which regularly schedules free screenings at the Marquee in Union South. And of course, the Wisconsin Film Festival will be running again in April of 2007.
I'll put a link to the Summer at the Cinematheque, and perhaps someone can see why I was unsure of the pronunciation of
Yeah.
Cinematheque in its true form, but that's awesome. What a perfect way to start off the summer.
Yeah.
Well, if there aren't any questions in the chat, we can go ahead and wrap up. But thank you again, Pete, for this awesome presentation. Thank you all for attending. And thank you for sticking around to the end of the conference. This was an awesome year. There were some tech issues along the way, but all of the sessions were really, really wonderful. So thank you all again. I hope you have a wonderful weekend, and we'll look forward to seeing you next time.
Thanks.